This is what the reading quiz, the OpenStax tutor. It's just in the cupboard in my office. It's just on the shelf there. So I got my password stuff, so I got my phone. I also called the bookstore. The lab guides weren't there, at least when you started the test. So this is what the OpenStax tutor page looks like when you come here. The yellow ones are the reading quiz ones. Now I show all of them. You can see I've got stuff all in there already. This one here will open up tomorrow morning, so you can do the one for Friday's lecture starting tomorrow morning. And so this one here is the one that you should do for Wednesday before class. And the blue ones, the SHWs, what are those for? Supplemental. They're not required. They're things I'm going to look at for helping guide me in choosing my questions for the test, but you are not going to ever be graded on those. So if you feel you know the stuff, there's not a lot of point to them. If you feel like you could use some extra problems, those are some extra problems. Emily?
Are they open?
Yes, the SHWs are all open.
Are they always going to stay open, or are they closed also when you submit?
I think they always stay open. I mean, you can always go back and look at them and still modify them. You know, the way the grading works is you can set it so the grade doesn't count after that, but really who would care if the grade doesn't matter anyway? So you should be able to still modify it. Okay, so just wanted to make sure that we do look at that. Next thing, let's go to the lab guide. The lab guide, here we go. Now the lab guide, which all you have is through what I'm going to be going through here, 2018-19 version. It's a little different than last year. I corrected some errors and so on. I'm not going to go through that. The lab reports is an important thing. The lab reports, a few years back, I changed over to, you don't have to have a lab book or anything. You just do it on whatever paper you have available to you. Scans PDF and you turn that in. So there's no special book for the lab report, but there is a special format. And so the first thing here is you'll have the title at the top of the page. The title is just the title of that day's lab. So today's title, what is the title of today's lab? Measurements? Okay, so you just have measurements at the top. Then, I don't care if you put on the left, right, or center, you should have a block where you have your name, your partner's name, something to designate this is me and this is my partner, just because every now and then it gets confusing. We upload these all to a site, and sometimes it's not clear whose paper it is. So make sure something designates, this is me, this is my partner, and the date you do it. Now, there's like 2 points for the title and 3 points for the name and date. Those should be automatic points, right? You shouldn't be messing those up. Then you have the purpose. The purpose, you can just quote the purpose that's in the lab guide. Those things are short. It's just, why are you doing this lab? I want students to always understand there's a reason for these labs. They're not just random busy work to keep you occupied because I have to get you in here for a few hours every week. Then, and I think it's another 5 points for the purpose. Then you come to the thing that will take the most time, at least initially, the scientific method portion. The scientific method, remember I talked about the scientific method is what defines science. And the basics of the scientific method is you observe something that you are finding interesting. You observe something like, you observe that the sun comes up in the east. Anybody ever seen the TV show Street Smarts? Nope. Well, it's a TV show, a game show, where they would ask people questions, and they would try to find the stupidest people possible. And they would ask them questions, and then the contestants in different rounds, one round is like, how many people got it right? And the next round is, one person got it wrong, which one was it, and so on. And they asked them ridiculously simple questions. And here was one question, I kid you not, they asked. In the northern hemisphere, the sun rises in the east and sets in the west. Where does the sun rise in the southern hemisphere? That was one where we had to guess how many people got it right. How many out of 3 people do you think would get that one right? one. I tell you, they find some dumb people, right? The sun rises and sets because the Earth's rotating. The direction the Earth is rotating stays the same no matter where you are on the Earth. But you observe something interesting. Let's say you didn't understand it was because the Earth is rotating. You say, wow, the sun rises in the east every day, sets in the west every day. Why is that? Ask a flat earther. They'll give you an alternate opinion. But you start with observing something interesting. The next step is the thinking about it, coming up with a hypothesis, an educated guess as to why you think that occurred. And so, of course, I already told you what we believe the answer to be, the scientific answer. The one that's been tested so many times, it would be just too shocking, we would all die if it turned out to be wrong, if the Earth is rotating. But you come up with this hypothesis that's based on scientific knowledge. So, you have some other experiments or things that have been done before you that said you have this going on, and then you say, well, because of that, then this should be doing. So your hypothesis needs to explain why the observation occurs and make testable predictions that are different than the observation. And then you have the test, which is a test of a prediction. So what we're going to be doing today, and we are just going to be doing the beginning part of the lab. Just for time's sake, I'm cutting out everything except for the dropping a ball part. So we're going to drop a ball, 1 meter, measure the time, 2 meters, measure the time. That's going to be actually the test you do. I've specified the test you have to do, and your hypothesis has to be something that would test a prediction of. And so first you have to have an observation about something falling. Now, of course, there is something that's a little contrived, because I've told you your observation has to be about something falling. So I believe I have an example observation here. When my roommate slams the door, my phone sometimes falls off the shelf. I can catch it if it's on the higher shelf, but I can't catch it if it falls from the lower shelf. Just an observation. If it falls from the higher one, I can catch it. It doesn't shatter. If it falls from the lower one, I can't get there. And so then my hypothesis needs to be something that explains why can I catch it from the higher shelf but not the lower shelf. And so I've given a potential hypothesis here. My hypothesis is boldly incorrect. Right? This is not intended to say, oh, here's the answer, because I want you guys to think it through. Right? So don't put this for your hypothesis. It's very wrong. But I said, because of constant air resistance, the speed of the falling ball decreases linearly with distance as it falls. Right? That's saying the ball starts off going fast, it slows down slower and slower and slower as it falls. I think you can all recognize that's a false hypothesis, right? But it's based on a scientific idea. It's based on, we know that there's air resistance that's going to oppose the falling ball. So there's taking some scientific information and making a hypothesis, guessing to that's why what I observed happens. And so my hypothesis makes a prediction. And you have to choose a hypothesis that's going to make a prediction that you can measure if the time to fall 2 meters is exactly twice, and when I say exactly twice, within uncertainty measurement, the time it takes to fall 1 meter, less time than twice or more time than twice. So there's only 3 things you're going to be looking for. Was it longer than 2 times, equal to 2 times, or shorter than 2 times to fall 2 meters as compared to 1 meter? And so this, since I said it goes slower and slower as it falls, it would take more than twice as long according to this hypothesis. And so then my test is going to be to compare. So if I scroll down, my test will then be to compare. I didn't write out a statement of the test here. But to compare the times, and if the time is longer than 2 times the 1 meter time, as the time to fall 2 meters is more than twice the time to fall 1 meter, then my hypothesis has been confirmed. Is it proven correct then? No, it's never proven correct, but it's confirmed that this prediction was true. On the other hand, if it's exactly twice as long or shorter than twice as long, then my hypothesis has been disproven. You can always disprove a hypothesis if it's the right experiment and it's a wrong hypothesis. So in this case, my experiment would surely have disproven my hypothesis. That's how the testing goes. So for every lab, you're going to have, well, almost every lab, you're going to have something like this. Starts with an observation of something relevant. There will be some kind of clarification of what your observation or hypothesis has to be, so it guides you a little bit. And then you have to have a hypothesis that explains why the observation occurred based on some scientific ideas, the theory of the day, and then a prediction that it makes that you can test and how you're going to test it. Is that clear? Okay, Emily.
So is that 2 hypotheses?
No, just one hypothesis. And the way the scientific method goes, if you disprove your hypothesis, you'd go back and make a new one. Well, we're not doing that because then we get into the endless cycle that science is. The research I did for my PhD, it's extensions of that are still going on because you just keep building. Other questions about the scientific method part? DJ.
So the only difference I'm getting from observation and the hypothesis is that hypothesis is scientifically based, whereas observation is just experience.
No.
Based off experience.
The observation is just an observation, like you said. And then hypothesis is based on a scientific idea. This is why the thing happened that I observed. So that why part's real important. And then it must be able to make predictions for other cases that you can test.
Okay.
Now, with these, if you have me read it and I sign off on it, and I believe we will have a TA starting next week. Really excited about that because I didn't have one last year. Then if either of us read it and we say, yeah, that's good, and sign off on it, that means you won't lose any points for the statement of your scientific method part. Right? If you don't have a sign off on it, you could still get a perfect score on it. It's just you don't have that guarantee. That doesn't mean you're going to get a perfect score on the testing part of it, the application, because that's another thing. Next, the equations. Any equations you're going to use in the lab. For today's lab, because I've cut things off, there are no equations. But you list every equation you're going to use and make sure you define the variables in those equations. Also, for every equation that you use, down in the calculations, you need to show one example of using that equation. Now, I am a very, very firm believer in spreadsheets. If you do a calculation 3, 4, 5 times, it's much easier to just make a spreadsheet, put the formula in, put your numbers in, boom, they're all calculated, and you don't have to do it all over and over again. I just want to see that you actually can put the numbers in once for each equation. So don't sit there and write out all of your calculations, just one example of each equation. Apparatus is the list of the important stuff you're using. For today's lab, we're really not using much important. What you're going to list is, meter stick, actually, meter stick and 2 meter stick. Going to use those so we can measure distance. Going to have a little ball, a steel ball bearing, and a timer. That would be your apparatus. The timer is actually on the computer, probably. You can use, if you have a timer that measures to thousandths of a second on your phone or your watch, you can use that. But if it only measures to hundredths of a second, I want to use the one on the computer just to give us one more digit in our numbers. Given your reflex time, that digit may not be very important, but it at least has some semblance of importance, and that's why I want you to make sure you have the thousandths on your device. Okay, then the procedure. The procedure should not be writing down the procedure that I wrote in the lab guide. As you probably have figured out by now, I can be really verbose. I have lots of long instructions. Try to make it as clear as I can, which I know sometimes makes it more confusing when you have so many words. But I want you to write a procedure in a succinct way that has enough detail that somebody else could read your procedure and do the experiment. So the goal is to have enough information for somebody to be able to repeat the experiment, but not have all of the extra explanation that I put in there to try to make sure there's no mistakes.
Can you use shorthand notation or abbreviations for things?
I was like, shorthand, like Greg method? No, make sure that it's readable, okay? So, don't have like R for the word R, Not like people text message these days.
It'd be like, for instance, for chemistry, BKR or beaker or something.
Well, sure, we'll never use a beaker, but yeah, I've had a student use NRG for energy, and yeah, I figured it out.
Okay.
But do make sure that people are going to figure out that it's not something obscure. Okay, then comes all done. Thank you. Then comes the data calculations and discussion section. This is the section where you actually start doing the experiment, and this should be a running dialogue of you going through the experiment. It's not just your data. When something goes wrong, you should write it down. When you're doing something, you should write down, now I'm doing this, right? So somebody can read through and follow what you were doing through the lab period. Every time you put in data with more than one measurement, which is almost every single time, put it in a data table. Don't have text, measurement number 1 this, measurement number 2 this, measurement number 3 this. That is very hard to decipher. You put in a table, you can glance at it and see trends and get everything in your head quickly. So you'll lose points if you don't put the data in data tables. Also, units are real important. Remember, I had in my little scrapbook example the Mars climate surveyor that crashed because of a unit problem. And if I were to tell you that my new home in South Park, yes, South Park, is 8.5 away, you would be probably just a little confused. 8.5 what? And what's the answer, Nathan? 8.5 what?
I got distracted.
Yeah. 8.5, I got distracted away. It's 8.5 hours away. It's really beautiful there. I just wish I had a kid that was in grade school so they could go to South Park Elementary. But without having the units, it's very confusing. If I told you my house is 0.75 away, you'd probably figure out that's 0.75 miles. But it could have been 0.75 kilometers, or it could have been 0.75 hours. I'm way the heck outside and drive in from somewhere away. So units are very important. Every measurement, every number you have, if there are units, which usually they are, they should be listed with it. Right? So don't leave numbers without units. If you don't have units, one example without units will take off 2 points for the lab. I don't take it off more than once because you could very quickly just take off the entire lab on not having units if you did. Now, when you make a data table, that was not it. Here's an example of my data table. I put a title for the data table, and then I put column headings to say what I'm measuring. And notice I have right here, parentheses, kilograms. That's the units. kg is the standard unit for mass, kilogram. I also see now after I've already sent this to the printers, that I made a mistake, so I'd have to take off 2 points. You wouldn't know it, but those were grams, not kilograms. You need to have the right units. I'm so embarrassed, but I can't lie to you, just pretend it didn't happen. It happened. So make sure you have the right units. This one here has something additional. Plus or minus 0.1 centimeters. The purpose for the part of the experiment we're doing today, that's the only purpose really, is to understand uncertainties in measurements. So here I was measuring the length of a spring, and I was having to eyeball where the bottom of the spring was. I'm not as precise in measuring when I'm having to eyeball it than I would be if I had something that was clearly defining where the end is. And so my uncertainty in the position of the spring, 0.1 centimeters, that's a bigger uncertainty than I normally would have had. I normally would have had something like 0.03. But I have 0.1 because I couldn't be as precise in my measurement. So I'll talk about that a little bit more. But anytime you have a measurement, so this is for measurements only. You need to have an uncertainty to tell the person who's looking at the data how much significance that data has. Now, there's something else important there. If I have plus or minus 0.1 centimeters, all of my numbers had better have the same decimal place as that shows. Right? If I had, you notice the trial 2, 130.0. Why do I have that 0.0? Because that 0 is meaningful. It's not 130.1 or 130.2. It's not 129.9. It's 130.0. If I left off the 0, for all you know, it could have been anywhere between 129.5 and 130.5. So don't drop off trailing zeros that have significance. And don't overspecify either. If I'm plus or minus 0.1, what would be the purpose of having 0.73? That 3 would be meaningless because I've already said I have no idea. My uncertainty is bigger than that number. So your uncertainty should match that decimal place. Notice it's a nice, neat table. Now, what was measured? This was the only thing that was actually measured in the experiment. I had the trials. I hung the masses on there. The masses were these self-same masses that I was hanging on there. And so I didn't measure these masses. I trusted them. That's why there's no plus or minus written. I just trusted them. I said, it's the 20. The stretch is calculated from the position. Because it's calculated from the position, I didn't put a plus or minus there. We're only putting the plus or minuses with the measured values. After that, we're just going to use our significant figure rules to keep track of how many digits we put in our numbers. And so I have my calculations here. This one does have one too many significant digits because there's only 2 here and I put 3 there. Okay. Sometimes that's the wise decision. Significant digits, say bye to mom. You guys know that Nathan is my son, right? Just in case there's any confusion. I certainly shall try to show no favoritism, but he's still tried my life. Which doesn't make him feel uncomfortable at all. Anyway. Graphs. Graphs are another thing that we're going to do a lot of. You're not going to do a graph today, but I want to make sure we've covered this. When you make graphs, make sure you use rulers. Notice how my axes, I actually use rulers to draw the axes. I marked off numbers very carefully. I made my graph so it's like half a page. And then I plotted my data points. So my data points, I put a dot and a circle around each data point, and then I drew a line. Now my data here was pretty close to a straight line, but when you find the line for a graph, there are some definite don'ts. Don't connect the dots. Your line should definitely, if you're, let's suppose that your data looked like, when I'm drawing my line, straight edge never works on the screen, just for the record. This would be horribad. I want to draw a straight line that best approximates the data if I'm trying to draw a line. So you don't connect the dots. Here's an equally bad way of doing it. Well, let's just connect the first and the last one. That's also equally bad. I ignored one data point. What you want to do is to find the line that comes the closest to all of them. Mathematically, we calculate with what's called a least squares fit. They use a computer algorithm to calculate, okay, so if I make the line like this, then if I take the distance perpendicular from the data point to the line, and if I square those distances in green and take the average of those, if that's minimized, that's what we consider the best fit. So I'm going to have you do graphs by hand so you can get the hang of actually finding the graph. So remember those. To do it with straight lines, use rulers, measure things carefully. Make sure you have a title for the graph that tells you why the graph is there. A lot of people have learned somehow to say, oh, this is the spring stretch versus spring force. Well, that's what the axis titles tell you. Having a title for the graph that tells me what the axis titles tell me is absolutely useless. There's no point to it. You want the title to tell the reader, this is what's important about the graph. This is why I made it. And so I have their title, Finding the Spring Constant, because that's why I made it. So make sure you have a title that's useful, that tells you why it's made. Then finding the slope. Once I've made that best fit line, I want to find points on the line that are going to be easy to read. So I had this line and I looked very carefully and I decided, come into focus. I decided that that was a little bit above the crossing, not so easy to read because it's just a little bit off. I decided this one down here, not there. This one right here looked to be right on it. Of course, I put the X on and now you can't tell. But I decided that one was a better representation. I'd have less error in reading that point because I want to accurately find the slope of the line I drew. Usually, your actual data points don't fall exactly on the line. And because they don't fall exactly on the line, you shouldn't use them to find your slope. Now, sometimes they do. In this case, my data was really good, made me happy. But I will still take off points if you choose one of your data points to find the slope, because in general, the data point's not on the line. And so just to protect you from making a mistake, I say don't ever use a data point that even if it falls on the line, for find the slope. Is that clear? Right? Because I don't want to take off points. I want people to learn good habits. Another rule of thumb is to try to make the 2 points you use as far away from each other as possible. And so this one over here that I rejected because I didn't think it was very good, it would have been a great point. It just didn't look like good enough crossing. Because if your points are far away, then your error in measurement will be a smaller percentage of the actual rise or run. Once I've identified my 2 points, I just found my slope is rise over run. You can see right there, rise over run. So that's another thing that's in the data section in many labs, not today's, but in many labs. So I just want to make sure I go over that. Let's go back to talking about the lab write-up. Yes?
Do you usually just do the rise over run the slopes right onto the graph?
I usually just do it on the graph, yeah. And so that's my calculation, right? Because it's still in the data calculation section. Question?
I know this is going back and get, but what's the difference between test section and procedure section?
Okay, the test section is just testing your hypothesis. The procedure section is what I told you have to do for the lab. So sometimes your test will be additional to what's in the procedure. Sometimes your test will be within the procedure.
Okay, so the procedure is textbook based, whereas the
test is based on your hypothesis. Yes, that's right.
And when you do the test, you have to actually do the test before you do your procedure?
No. You just have to do the test before you're done. The timing of when you do the test, usually you're doing it at the end, but it's up to you. Okay, one last thing here. What if you make a mistake? What if I had made a measurement? So as you're making the measurements, you're putting them in your data table. What if I made a measurement and I was like, uh-oh, that 136.2 was wrong. I made a mistake. The correct thing to do is not white out. That is shameful science practice. That's pretending that you didn't make a mistake. In science, you keep that data. You don't want to use it, so you do something like you draw a line through it. Okay, that went through half of it. Draw a line through it and say, don't just say bad data either. Say, I made this mistake. And of course, this would be defined, not the word this. When I was in graduate school, we had an example of a student who was not very good with this scientific integrity. If he did an experiment and the outcome wasn't what he wanted, he would throw the data away and write in the lab logbook for our experiments, bad data. Well, you know what you have there? At the end, if you find, 5 experiments that back up what you want and 21 that said you're wrong, you threw away all the 21 and you go publish, look, I was right. But you clearly have data that says you weren't right. And actually, when I came here to uni, we had a teacher who pretty much did the same thing. Like, that's not honest science. I cross it out, I give the reason I cross out, but it's there, anyone can see it. Sometimes it turns out what you thought was a mistake wasn't a mistake. You don't want that data gone. Okay.
So do you just add it to the bottom of the table at that point?
Yeah, if I have to go back and remeasure, yeah, just add it to the bottom table. Or you might have to make a supplemental table. One thing I forgot to mention, a schematic diagram should be included to illustrate how you set up your equipment. So as you saw in my example here, I had a diagram for how I did the first part and a diagram for how I did the second part, so that somebody can look at it, look at the words, and figure out, yeah, that's what he did. That's, by the way, the lab we're not going to do because we're going to go to defy gravity instead. But if I figured I'd use that one so you don't have a lab write-up of a lab you're going to do. All right, to the results. As you're going through your data calculations and discussion, data calculations, I'll put them in a different order, you're going to be calculating results. The results section is where you summarize things that you calculated above that were important. So the results is not new things, it's the summary of the important things. So for instance, in today's experiment, you're going to be measuring the time it takes for a ball to drop 1 meter and the time it takes for it to drop 2 meters. And so those are going to be your important results. Plus, if your hypothesis was confirmed or disproven. So I think that's the only 3 things for today's results because of the stuff I've cut out. So it's just the important things, not all the numbers. You don't have all of the times you measured, just the average for each one. Then conclusions is where you write down the things that you learned, what went right, what went wrong. Like if there was really a problem that could have been, lab would have been so much easier if there had been 5 more words in the lab guide or this small change. Put that in the conclusions. If everything went swimmingly, put that in there. I love to see that, it happens every now and then. And make sure you have what you learned. Was the purpose, achieved? Did you learn what the purpose was for you to learn? And finally, how did you determine if your hypothesis was confirmed or disproven? That should be in the conclusion section. So the conclusion section is what you learned. That's 20 points, 1/5 of your lab right there, what you learned. 10 points in the results, I think it is, just summarizing the important outcomes. 20 points in the data calculations and discussion, for all your data collection. So yeah, here's a practice lab write-up that I did. Actually took me forever because I've got my problems. And something I'm really not proud of, but I'm going to point it out anyway. Okay, in the lab guide, you'll have questions that are marked Q/C with a number. For those, list them QC1, so I know when I'm grading. That's where he answered that question. But your answers should be standalone answers. I shouldn't have to look back in the lab guide to see what the question is you're answering. So if you look at my answer here, it doesn't say it's a straight line. It says the graph shows a straight line relationship for all but the data points with no weight, or the data point with no weight. I don't have to look at what the question is. The answer stands alone. The QC stands for question/comment. So make sure you're not just answering the question, but stating it in a way that the person doesn't have to look at what the question was. Data table 2, calculations. Here's my sample calculations. Hypothesis test. Here's my data. Hey, I got the right units this time. My results, succinct results. My conclusions, I was somewhat succinct there. My graphs, and here my big embarrassment. This line here is supposed to be a perfectly straight line. I had made a mistake. I noted my mistake. I redid it. And then when I went to save my graphs, I threw away the new graph and kept the old graph. At that point, I wasn't going to redo everything. So I said, well, I'll take the 5-point loss and just put in this figure. I did it. Here's my explanation of why I have the wrong graph. Sometimes you have to make a decision for time to lose a little points rather than spend another 20 minutes to redo the experiment. Okay, here's instructions for scanning. I'll skip over that. Here are the actual breakdowns for all of the points. So you can see what's important. Actually, conclusions is 15. I was wrong. I said 20 is 15. So there's how the points are divvied up. you should definitely get all the points for those things, right? Those 15 should be a given. If you didn't, it's just sloppiness. Now, the scientific method, if you get that signed off, you'll get the 20 points. Then you have the procedure, data, results, and conclusions. That's going to vary from student to student for sure. So any questions about the lab write-up at this point? Yes?
Are you wanting us to, what specifically do you want done ahead of time before we come into lab?
I don't require anything. It would be, you would be best served to go through and write up everything before the data calculations and discussion, because you can do that beforehand. Except for every now and then I do something like I did today, and I cut out part of the lab. Well, of course, if you have that written in, you can just cross it out. So it's going to save you time for the lab. But obviously, you can't have anything after that. Okay, so let's get to today's lab and get started. So today's lab, activity 1, measurements. Our purpose is to learn to read some simple instruments. Okay, we're only learning to read meter sticks here because of my change. And how to handle uncertainties. That's our key thing here, handling uncertainties and measurements. So every measurement is going to have some uncertainty. I have, things in here like, how old is a person? If you start getting technical, you realize there's no way to get the exact age of a person. You have things as simple as how do you time the beginning of the life of a person? Is it at fertilization? Is it, when you have the head crown? Is it when the whole body's out? You can't have it exact. And so for every measurement, we're going to have to take into account things that could cause errors. So things that could cause errors. Let's start with the meter stick. These meter sticks, the ends are all rounded up and stuff. So the ends are probably not good. To make things worse, almost always, they don't even calibrate the ends of the meter sticks. Oftentimes, you'll see the meter sticks got like an extra 0.5 millimeter beyond the 0 mark. So if you measure like this, you already have a problem, right? You already have an uncertainty because the meter stick's end isn't calibrated. Because of that, usually, for today's lab, we're going to do that. For today's lab, we're going to measure 1 meter to be the distance from the top of the meter stick to the bottom of the meter stick, which means we have a little bit of uncertainty that's introduced because of that problem. So what's my distance? Well, it's 1 meter, 1.00 meter. Figure out the distance to get the uncertainty. Plus or minus, and I have to say, well, I have the ends of the meter stick. If I put it together, it's probably about 1 millimeter of uncertainty for the ends of the meter stick. And then furthermore, when I have the ball, I'm just holding it. I could be off by another millimeter there, so maybe plus or minus 2 millimeters for the distance for today's measurement of height. Now, if I'm going to measure something more accurately, I can have something like, what is the length of this piece of paper? Well, if I take this piece of paper, put it on the meter stick, I can do much better. I'm not going to use the end of the meter stick because I don't want to have that uncertainty. So I put one end right on. In my case, I just generally use the 10. It makes it easy to subtract and get the answer out. I go to the other side, and I see that it's between 31, well, actually, it looks like it's right on 31.6. If it was a little bit off, I would then say, well, how much off would it be? And typically, I'd say I can probably estimate to about 1/4 of the distance between the lines here. So 1/4 is, of course, 0.25. I round that to 1 digit to make it 0.3. So 0.3 of that smallest thing, which in this case is millimeters. So I'd say plus or minus 0.3 millimeters is what I can measure the length of this paper to. And so that's a limitation of the instrument. When I was measuring the spring, like I told you, I was trying to eyeball where the spring length was. More uncertainty because I could be looking at different angles, have parallax. And so that's why I went with 0.1 centimeter or 1 full millimeter for my uncertainty because I had additional error. So you have to take into account the different kinds of errors you have. Now today we're going to be just dropping a ball and timing things. And so you're going to have somebody drops a ball, and you start a timer when they drop it. You stop the timer when it hits the ground. In that timer, the timer has an uncertainty of, since it measures out to thousandth of a second, we're going to say it's plus or minus 1 in the last digit the timer measures. But that's the timer. You, the person making the measurement, is a bigger uncertainty than that timer is. And so you have to think about, how off could I be in my timing and estimate your uncertainty in the timing. So let's go to what you're actually doing in the lab today. Okay, that's when you're upside down, sometimes you go the wrong direction. This is discussion about how we measure that. These equations, by the way, here are what you technically do instead of using significant digits to track uncertainty. You have your uncertainty, which is the delta. Delta x would be the uncertainty in x. Delta r would be uncertainty in the result. And if you have a measurement times a constant, the uncertainty in the resultant is the constant times the uncertainty in the measurement. Well, that was simple. If you have addition or subtraction, the uncertainty in the resultant is the sum of the two uncertainties. It gets more complicated, though, if you have multiplication or division. The uncertainty in the resultant divided by the resultant is the sum of the uncertainty of each variable divided by that variable's value. So basically, think about the percentage uncertainty is the sum of the percentage uncertainties of the numbers multiplied or divided. And this here is just a special case of that, right? X squared is x times x. So if I had delta x over x plus delta x over x, that would be 2 delta x over x, hence the n, 2. Yeah.
On that third one going down, why doesn't it matter if they're in the numerator or denominator?
Because multiplication and division are fundamentally the same thing. Division is just multiplying by the reciprocal.
Okay.
So that's why. Because it's still the same percent uncertainty then.
Okay.
So this is the way you technically do that. In this lab is the only time when we have that in this class, because it's kind of a nuisance. And we're not doing that part. So you're not going to have to use those equations. Hence, once again, not using the equations today. We're not using the vernier calipers because that's to measure the diameter of the balls. We are using the meter stick, meter ball. We're not using the triple beam balance. That's to measure the mass of the balls. So the only things here, meter stick, meter ball, and the timer I set. So what we're actually doing, notice here I have the specification of your scientific method stuff. We're timing, let me just point out where we're stopping. We are stopping after QC6. That's good because this page apparently is blank. Oh, no, it's not. Okay. So we are stopping right here. So what you're going to do is, and I want you to note the time or the order of these things because it's important, I think, for your thought process. Before you do any experiment, you want to estimate how long you think it'll take for a ball to fall 1 meter. So you're just thinking in your head, ball to fall this distance. How long do I think it'll take? Are you going to be correct? Probably not, right? I'm not expecting correctness here. I expect you to think about it and put what time you think it'll be and give your reason why. And then you're going to take a ball and drop it without timing this meter a few times and say, do I think I was close or do I think I was off? And so you're going to reevaluate after you've dropped it a few times, not timing. And then you're going to say, how off could I be? How many seconds off do I think I will be? So after you have first made your estimate, then dropped it a few times, made a new revised estimate, giving the reason you changed it if you changed it, or the reason you didn't change it if you did not change it. And then you've come up with an estimate of how long you think it's going to be. Then you're going to get to actually doing it. So actually, where's the first question here? Oh yeah, that right. So here's the first place where you're actually measuring anything. Now for the actual measurements, you're doing this in partners, in groups of 2. And so one partner, let us suppose that I'm working with Leslie. And so Leslie's going to take her data. When she's taking her data, I'm going to drop the ball. So I'm going to hold the ball here. You say, you ready?
Go.
And so I don't drop it when she says go. That means she's ready. I'm going to drop it. She's going to start the timer when she sees me drop it, stop the timer when it hits the ground, and then she's going to record in her data book, that's the time it took to drop 1 meter. And do that at least 3 times. Then you switch positions. So now Leslie's going to be dropping, I'm going to be timing. And writing down, each time I do it, make sure I write down the data. Remember, you have an uncertainty that you would just estimate. So you just put in your column header, plus or minus how many seconds. And then everything that's below it is understood to have the same plus or minus in the same units. So after we've each done that, then you're going to calculate what the average was in the standard deviation. And the spreadsheets, there's a spreadsheet on here, not great. I just had these things completely reinstalled with the operating system and everything. And one thing that's changed is now they go to sleep again, they'll have to log in again. We did have them set so they wouldn't log you out after sitting around. But there's a spreadsheet in, I don't have it there, so I can't show you. At the top right-hand corner of the screen, somebody who works for me put a folder that says PHYS 151. If you open that up, there's going to be a spreadsheet in there. Open the spreadsheet. There's a whole bunch of tabs. Well, there's like 5 tabs, different worksheets. The first one says statistics. Click on statistics. And then it has a place for you to enter your numbers and it calculates the average and standard deviation. Keep your number of significant, well, not number of significant digits, the least significant digit the same as what you have in your measurements. So for the average, just keep your decimal place the same. You see how I did there. And standard deviation likewise. So you should have a data table like this that shows your timing, your partner's timing. Notice I have plus or minus. I used 0.7 seconds here. That was just the number I made up for the purposes here. That's, I hope, not your value. Your plus or minus, there's no real right answer, but there's definitely wrong answers. Like if you say plus or minus 10 seconds, yeah, that's going to lose you credit. Everybody knows it's not going to be plus or minus 10 seconds for the time it takes for a ball to drop 1 meter. So make sure you have data in a table that looks something like this. Answer each one of these questions, and then you're going to drop it 2 meters. That's what's on this page. You only have to do 1 set of data for the 2 meters. You don't have to do 1 for each partner. And then you can analyze your hypothesis outcome. So any questions? Yes?
What does this do?
Okay, so what does this do? You should have everything done before you leave today. And I cut things down, so I think you will. And then it's due Thursday night before midnight. Okay, I'm going to open the door here to let some air in because I don't know about you, but I am sweating out too much. And I will grab some balls so you can start playing around with those, and then I'll relog in your computers.
For this lab, are we going to need the observation hypothesis test stuff
Yes.
as well?
Yes.
Okay.
Yes.
For the slide, you said that we can write on anything,
Yes, that's right.
and then we just turn that into a PDF.
That's right.
I was about to ask a question.
Okay, yeah. You write any paper, just you scan it as a PDF. Okay, so groups of 2, so you'll need to spread out a little since we are mostly in 3 people at a table. Yeah. Yeah, so open the door for the first question. And first. Okay, also something else I forgot to say, in that same place that you have the spreadsheet, at the bottom there's a little program that says timer. That's the timer to use if you don't have one on your phone that goes to thousandths of a second. And that timer is really simple. You press the space bar, it starts. Press the space bar again, it stops. Press the space bar a third time, it resets and starts with 1 motion. So you don't do a reset, you just, when you hit it again, it's going to restart at 0. Okay, here's, I put them away wet, now we're all rusty. Here's the stainless steel rusty balls. So each group of 2 should have one. So once again, break up into groups of 2. If I tell you the password, can I trust you to not type it in wrong?
Yes.
Because there's no real reason to have it secret. It's just that I've had people who enter in the wrong password and lock everyone else out. I'll just write it on the board. Okay, that's the password. PHYS number 4, capital W, win.